Your Copilot can talk, it understands your context, and it can even reason through multi-step problems to give you a response that feels human. But the moment you ask it to do something computationally heavy, everything falls apart. If you needed to validate data across 3 legacy systems, transform that data, and apply specific business rules before giving an answer, it hits a wall. That wall is the connector architecture. Standard out-of-the-box connectors are great for moving data from point A to point B because that is exactly what they were designed to do. However, they were never built for heavy computation or complex orchestration. They definitely weren't built to handle the deep business logic that separates a demo-friendly chatbot from a system that actually gets work done. The real gap here isn't between what Copilot can ask and what your data can answer. In reality, the gap is between what the bot can say and what your business actually needs to do. We are solving that problem today. We are moving away from a bot that just talks and building a bot that actually executes. The bridge to get there is pro-code Azure Functions, but they have to be architected the right way to work. Why standard connectors fail at scale? Most teams don't see this problem until it is too late to easily fix it. You start with a use case that looks simple on the surface, like a user asking about a specific invoice. To answer, the bot has to check 3 different systems, validate the information, and apply your business rules. Naturally, you try to build this using standard connectors. The first issue is that these connectors are built for simple data movement rather than complex logic. They are perfectly fine if you just need to get a record or update a single field. They are not fine when you need to transform data and check it against multiple systems to return a structured result. When your Copilot needs to perform real work, these standard connectors quickly become a massive bottleneck. You find yourself chaining them together where one connector calls another, and then that one branches off based on a dozen conditions. You end up nesting logic deeper and deeper, and every single new connection adds more latency to the process. This is what I call the latency tax. Every time a connector makes a call, you pay for the network round trip, the authentication, and the overhead of moving that data. If you have a complex workflow, it can easily take 10 seconds or more for the user to get an answer. To the person waiting, it feels like the bot has crashed, and usually they just give up and leave. Then you have to deal with governance and DLP policies. These rules are designed to stop data from moving between approved and blocked connectors, which is security doing its job. But this also creates silos where your finance tools can't talk to your HR tools without breaking a policy. You are constantly hitting walls that make sense for protection, but absolutely poison your technical architecture. At the same time, the low-code expressions in Power Automate have very real limits on what they can execute. You can handle basic string changes or simple logic, but they aren't built for heavy lifting or consuming external APIs efficiently. They simply weren't designed for the high-level work that your business actually requires to function. Because of these limits, teams start building messy workarounds. They create nested flows that call other flows or hide data in queues to try and delay the work. These integrations are brittle, and they break the second your business requirements change. You are essentially trying to solve a connector problem by stacking one workaround on top of another. The reality is that none of this is maintainable or scalable because it isn't a real engineering solution. The core problem is that you are trying to do pro-code work using low-code tools. Connectors aren't bad, but they are simply the wrong tool for this specific job. What you actually need is total control over your environment. You need type safety, enterprise libraries, and the ability to use caching strategies or connection pooling. You need retry logic that actually understands your business and monitoring that catches a bug before a user ever sees it. That is why we use Azure Functions. It gives you a blank canvas where you use your own language and your own libraries. Your logic sits right next to the Power Platform, but it stays connected through a hardened, secure gateway. On paper, this architecture looks simple, but it is often very hard to execute in practice. That is exactly what we are going to fix right now. The architecture choice, where the rubber meets the road. So what is the actual alternative here? It is not about replacing the Power Platform entirely, which is the exact mistake most teams make the moment they hit a wall. They assume the only answer is to rip everything out and rewrite the whole system in .NET. But that is not the right move. The real answer is to extend the Power Platform with the very things it was never designed to handle in the first place. Azure Functions sit entirely outside that low-code perimeter. They are not part of the Power Platform ecosystem, they are not governed by those same restrictive rules, and they are not throttled by those frustrating execution limits. Think of them as a blank seabed canvas where you can write real code that is type-safe, fully testable, and connected to your existing enterprise libraries. They provide everything that Power Automate expressions simply cannot be. But here is the critical part of the strategy. These functions are not disconnected from the Power Platform either. They plug right back into it through a clean interface using OpenAPI specs and custom connectors, which acts as the handshake between these two different worlds. When your Copilot asks the Power Platform to perform a task, the platform does not struggle to do it with standard connectors. Instead, it calls your function. Your function handles the heavy computation and returns structured data, and then the Power Platform passes that result back to Copilot. The entire process feels completely seamless to the person using it. This is what we call the Fusion developer model, and it is quickly becoming the standard for enterprise AI because it is the only architecture that actually works when you try to scale. Now, Azure Functions come in a few different flavors, and choosing the right one is the first real decision you have to make. You have the consumption plan, which is the original serverless model where the system scales all the way down to 0. You only pay for what you actually use, but the cold starts are absolutely brutal, and we will come back to that specific problem in just a minute. Then you have the premium plan, which uses always-on instances that stay warm, so cold starts are never an issue. The downside is that you are paying a baseline cost regardless of how much traffic you actually have. If you are building a Copilot plugin that only gets called during normal business hours, that becomes a very expensive way to operate. Finally, you have Flex consumption, which is the new default as of 2026 and the right choice for almost every Copilot architecture. Flex gives you the best of both worlds because it is still serverless and scales dynamically, but you can configure always-ready instances that stay warm. This creates a small pool of workers that are always initialized and ready to serve requests immediately. The baseline cost for an always-ready instance is about $0.000004 per gigabyte second, which is 6.5 times cheaper than on-demand execution time. You get those warm starts without the massive premium price tag. Why does a warm start matter so much for a Copilot? It matters because cold start latency is catastrophic for interactive AI. When a user types a question, Copilot processes it and calls your function, but then your function has to wake up. It has to load the runtime, initialize every dependency, and deserialize the request before it even starts running your code. This entire process can take 5 seconds or more from a cold start, leaving the user staring at a loading spinner until they eventually switch their mental context. By the time your function finally returns a result, they have already moved on to something else. Flex with Always Ready completely eliminates that friction. Because your instances are already warm, the runtime is loaded, and your dependencies are already initialized. When a request comes in, your code runs and the response goes out with sub-100 millisecond latency. The user perceives the interaction as instant, which is exactly what you want. Using C+ in an isolated worker model gives you a level of control you just cannot find anywhere else in the Power Platform ecosystem. You get type safety from the compiler, testability through dependency injection, and access to any NuGet package you might need. You can use the exact same libraries your backend teams are already using, like Entity Framework for database queries, Poly for resilience, or OpenTelemetry for instrumentation. You can even manage your secrets through Key Vault, providing everything a real production system actually needs to survive. The connection between your Copilot and your function lives and dies by the OpenAPI spec. This is a critical piece of the puzzle that we will spend a lot of time on later. The OpenAPI spec is not just a piece of documentation, but rather the semantic contract that tells the LLM when your function is relevant and exactly how to call it. If you write a poor spec, Copilot will not use your function even when it should, but a well-written spec ensures Copilot calls it reliably and passes the correct parameters every single time. Your function lives in Azure while your Copilot lives in the Power Platform, and they communicate through OpenAPI and custom connectors. You write all the complex logic you need in CWise, while the Power Platform handles the orchestration and the conversation flow. This clear division of labor is what separates a working, professional plugin from a collection of janky workarounds. It might not be the sexiest solution, and it is not purely low-code or purely pro-code, but it is the real answer to the problem. The cold start problem and why Flex consumption wins. Cold start is not just a minor latency issue, but rather a massive invisible overhead that triggers every single time your function wakes up from a nap. To understand why this happens, we have to look at what occurs when a function goes cold. Because nobody has called the function recently, Azure has scaled your instance all the way down to 0 to save resources. When a new request finally arrives, the platform has to allocate a brand new worker, start the net runtime, and load your assemblies from the disk. It then has to perform JIT compilation on your code and initialize your entire dependency injection container. It still has to establish connections to your database, your cache, and any other external services before a single line of your business logic even starts to run. On the original consumption plan, this entire sequence happens on every single request whenever your traffic is sparse. You are paying for compute time from the very moment the request arrives until your code actually finishes executing. For a typical net function using a few enterprise libraries, that overhead usually lasts between 1 and 5 seconds. If your application has heavy initialization requirements, like loading machine learning models or building large dependency graphs, that wait time can easily stretch to 10 seconds or more. The timeline for the user is just brutal. They type a question, Copilot processes it, and then your function takes 2 full seconds just to wake up. Even if your business logic runs in a lightning-fast 100 milliseconds, the total perceived latency is still over 2 seconds. The user notices that delay, the bot feels sluggish, and the frustrating part is that nothing in your actual code is slow. The problem is entirely tied to the initialization process. This is the exact point where Flex consumption diverges from the old way of doing things. Flex introduces the concept of always-ready instances, where you configure a minimum number of instances that stay perpetually initialized. These instances never scale to 0, so the runtime stays loaded, your dependencies stay ready, and your database connections stay pooled. When a request arrives, there's no startup overhead at all because your code runs immediately. We start measuring latency in tens of milliseconds instead of seconds. The cost structure is what makes this approach economically sensible for most businesses. Always-ready instances are built at a baseline rate of approximately $0.000004 per gigabyte second even when they are sitting idle. That is incredibly cheap. If you run a single always-ready instance with 512 megabytes of memory, you are looking at a bill of roughly $15 per month. When you compare that to the premium plan, where the smallest tier keeps instances running at a much higher baseline cost, Flex becomes the obvious choice for anyone who is cost-conscious. Here is the key insight you need to remember. Always-ready instances do not eliminate the cold start problem for every single scenario, but they do eliminate it for your baseline traffic. If your Copilot generates 10 concurrent calls and you have 2 always-ready instances, those first 2 requests will get warm performance. The remaining 8 requests will trigger new instances that have to go through a cold start. In the real world, most concurrent Copilot calls stay within your always-ready capacity and feel instantaneous. You only see minor startup latency when your demand genuinely exceeds that provisioned baseline. The premium plan takes a much more aggressive approach by keeping minimum instances running at all times without any scale to zero behavior. Cold start is eliminated across all of your traffic because those instances never go idle, but you definitely pay for that guarantee. You are stuck paying an hourly rate for reserved compute regardless of whether your function handles 0 requests or 1,000. If you are running a use case that only happens during business hours, that pricing model simply does not make sense for your budget. Flex with 1 or 2 always-ready instances hits the perfect sweet spot for most enterprise teams. Your baseline Copilot traffic gets handled with sub-100 millisecond startup latency, while your burst traffic scales dynamically without you having to pay a massive premium. Your monthly cost stays reasonable, and you have successfully eliminated the single biggest performance problem that plagues serverless AI applications today. This is the very first technical decision that separates a real production architecture from a simple prototype. OpenAPI specs, the bridge between code and AI. Now we get to the craft that actually separates a working plugin from a broken one. Your Azure function might be fast, your always-ready instances are warm, and your COS code is solid, but none of that matters if Copilot never calls your function in the first place. That is the job of OpenAPI. It tells the AI when your function is relevant and exactly how to invoke it. But here's the problem. Most developers treat OpenAPI like documentation or something you generate after the fact just to keep the API docs in sync with the code. They see it as a boring checkbox on a deployment checklist. But that is not what OpenAPI is anymore. In reality, OpenAPI is the semantic contract that the language model uses to reason about your function. It is the specification the AI reads to decide whether to call you at all, and it serves as the instruction manual for filling in parameters and interpreting results. The distinction matters because documentation is written for humans, while OpenAPI specs for Copilot need to be written for models. Those are not the same thing. Power Platform currently standardizes on OpenAPI 2.0, which you might know as Swagger, though support for 3.0 is expanding through 2026. If you are building a production plugin today, you should target 2.0 for broad compatibility. The concepts we are discussing apply to both versions, but the tooling landscape still leans heavily on Swagger. It starts with the operation ID. This is the identifier for each endpoint in your spec, and it needs to be stable and verb-based. It should describe what actually happens rather than what the internal code does. If you compare validate invoice against process v2, one tells the model exactly what to expect while the other tells the model nothing. The model will try to choose correctly based on context, but if you force it to guess, it will eventually guess wrong. When that happens, your entire plugin fails silently. Descriptions are where most specs fall apart because developers write descriptions for other developers. They explain how the endpoint works, the response format, or the parameter validation rules. But the model does not read like a developer reads. The model needs to know when to use this operation, what user intent triggers it, and what specific problem it solves. Compare 2 descriptions of the same function. One says, returns invoice data from the accounting system, while the other says, use this when the user asks about a specific invoice to retrieve details including amount, date, vendor, and payment status. The first tells the model nothing useful, but the second tells the model exactly when to call this operation. Parameter descriptions work the same way. You are not writing for developers who can infer the intent, but for a model that will pass your description to fill in values. You need to be explicit about format constraints. Instead of just saying date, you should say invoice date in ISO 8601 format, and do not use relative terms like yesterday or last quarter. The model will try to send relative terms if you do not explicitly forbid them, and you want to prevent that failure before it happens. You also need to include examples. Do not just provide one, but use multiple examples showing realistic inputs and outputs. The model uses these as demonstrations of correct usage, and a well-crafted example is worth 1,000 words of explanation. Response schemas also need to be complete. You should define every status code your function can return, including 200 for success, 400 for validation errors, 404 when the resource is missing, and 429 when rate limits are hit. For each response, you must describe what it means. The model uses error schemas to understand failure modes, so if you do not define what a 400 error looks like, the model cannot learn to anticipate failure. It cannot adjust its behavior, and it cannot explain to the user why something went wrong. This is the bridge between your code and the AI. If you get it right, Copilot will use your function reliably, but if you get it wrong, your function will sit unused even when it is the perfect tool for the job. The irony is that this spec is often more important than the code itself. Writing OpenAPI for LLM reasoning. Most teams skip this step because they assume that having a technically correct OpenAPI spec is enough. It isn't. The model reads your description like a user reads documentation, so if your language is vague, the model makes vague inferences. It misses context and calls your operation when it shouldn't, or worse, it doesn't call your operation when it absolutely should. One level deeper, we have the problem of operation collisions. This happens when you have two endpoints that sound similar from the model's perspective, like get customer by name and search customers. Both retrieve customer information and both accept a name parameter, so the model has to choose which one to call based on your descriptions. If those descriptions are interchangeable, the model will pick randomly and half your queries will go to the wrong operation. The fix isn't to rename everything, but to be explicit about the scenario each operation handles. Get customer by name should say, use this when the user provides an exact customer name and you need to retrieve a specific record. Meanwhile, search customers should say, use this when the user is asking about customers but hasn't specified a particular name, such as when they ask to see customers from a specific region. Now the model can differentiate and it will choose correctly. Parameter examples are also non-negotiable. While standard documentation might include examples, OpenAPI specs for Copilot must include them. The model uses examples as demonstrations of correct usage. When you write an example of 2024-01-15 for a date parameter, you are teaching the model that this is the format you expect. You are preventing it from sending yesterday or last month or any other natural language expression. A single well-chosen example prevents entire categories of failures. Error schemas get overlooked constantly because developers focus on the happy path. But the model needs to understand failure paths too, and it needs structured error information to do that. A consistent error schema with a code, a message, and details tells the model how to interpret failures. It learns to recognize when a call failed and why, which allows it to adjust its behavior or explain the failure to the user. Without that structure, errors become opaque and the model cannot learn from them. Consider a practical example where your invoice validation endpoint returns a 400 status when the invoice number doesn't exist. If your error response is just a message saying not found, that is technically correct, but semantically useless. The model sees a 400 error and knows something went wrong, but it doesn't know to ask the user for clarification or suggest trying a different number. Compare that to a structured response that includes an invoice not found code and a suggestion to check the number and try again. Now the model understands the failure mode and can recover intelligently. Finally, you must curate your surface area. The temptation is to expose every endpoint you have built because it feels comprehensive, but in reality that is a disaster. Every operation you expose adds cognitive load to the model, and every extra operation increases the chance of a wrong selection. Every unused endpoint in your spec is just technical debt. You should remove operations that aren't high value and hide internal administrative endpoints. Only expose what Copilot actually needs to do its job. This curation process is where your architecture becomes intentional instead of accidental. C# Azure Functions, the engine. Now let's talk about the actual code that powers this architecture. Your Copilot is fast, and your OpenAPI spec is semantic and clear, but the function itself is where precision matters. This is the code that actually runs. This is where the theory meets the work. HTTP-triggered functions are your standard entry point. Copilot calls an endpoint, your function receives the request, it processes data, and then it returns a response. This request-response pattern is fundamental. Everything else in this section is about making that cycle as efficient as possible. The isolated worker model in Net 6 and above gives you control that you don't get in earlier versions. You own the startup sequence and manage the middleware, which means you configure dependency injection at the application level rather than the function level. You control what gets initialized once per application lifetime versus once per request. This control is exactly how you eliminate startup waste. Here's the critical pattern. Use async and await throughout your entire stack. This shouldn't just be in your function handler, but in every layer from database queries to HTTP calls and cache operations. The reason is simple. Blocking calls waste your always-ready capacity. When your code blocks while waiting for a database query, that thread just sits there idle. A thread is a scarce resource, and your instance can only handle a limited number of concurrent requests before blocking starts queuing up the work. With async and await, that thread returns to the pool, so your instance can handle the next request. Your always-ready capacity suddenly serves 10 times the throughput. This isn't just a performance nicety, it is architectural. Without async, your cold start latency won't even matter because your warm latency will be terrible anyway. Next, let's look at singletons. Your HTTP client, your database connection pool, and your caching client should all be initialized once when your function app starts. Most developers get this right for the HTTP client, but they miss it for other clients. A database connection takes time to establish, and a Redis client needs to authenticate, so these operations are expensive on every new initialization. They are only cheap on the second call because pooling handles the heavy lifting. Dependency injection handles this elegantly if you register your clients as singletons and inject them into your function handler. Every invocation then reuses the same instance. But there's a counterintuitive pattern here. Use lazy initialization for expensive dependencies. If your function loads a heavy ML model on startup, that model consumes memory and CPU while it sits there unused. If only half your invocations actually need that model, you're wasting always-ready capacity on something that isn't helping you. The solution is the lazy pattern in CHOS. The dependency initializes on the first actual use rather than at app startup. Subsequent uses hit the cached instance instantly. This is how you keep cold starts low while still having access to heavy dependencies when they are needed. Ready-to-run publishing is another overlooked lever. It's a simple flag you set during the build process. Instead of your net assemblies being JIT compiled at runtime on the first use, they're pre-compiled ahead of time. Your function starts and all the code is already ready to execute. There is no JIT overhead and no compilation delay. For latency-critical functions, ready-to-run saves hundreds of milliseconds on a cold start. It also provides faster warm execution. It's a pure win, and the trade-off of a slightly larger deployment package is irrelevant compared to the latency gain. These patterns are not optional for production Copilot plugins. Using async throughout, singletons for clients, lazy initialization for expensive work, and ready-to-run publishing is the difference between a function that takes 2 seconds and one that takes 100 milliseconds every time. The actual business logic is usually straightforward. You validate invoices, query databases, or call downstream APIs. But the infrastructure around that logic determines whether your plugin feels instant or sluggish. This is where developers who understand serverless architecture separate themselves from developers who just run code in the cloud. Securing the function, identity, and network. A fast function that leaks data is worse than a slow function that stays secure. Performance is meaningless without a hardened perimeter. Your function lives in Azure, handles requests from Power Platform, and calls downstream systems. It touches sensitive business data. Every connection point is an attack surface. Every decision you make about authentication and network topology determines whether your plugin is secure or vulnerable. Start with identity. Managed identities are the foundational security pattern for Azure workloads. Instead of storing API keys or connection strings in your configuration, your function app gets an identity issued by Microsoft Entra ID. When your function needs to authenticate to Azure SQL or Azure Storage, it proves its identity cryptographically. There are no secrets to rotate and no keys embedded in code. There are no credential leaks waiting to happen because the Azure platform handles all of it. Your only job is to request the identity and assign it the minimum permissions it needs. This pattern extends beyond Azure services. If your function needs to call a REST API that supports Entra ID, your function simply authenticates as itself using that managed identity. It requests a token from Entra ID and passes that token in the authorization header. The downstream service validates the token and grants access based on the permissions assigned to your function's identity. The entire handshake is cryptographic, so no secrets ever touch your code. Now, we have to consider who can call your function. By default, an HTTP-triggered function in Azure is protected by a function key. It's a simple bearer token that you pass as a query parameter. Azure validates it, and while this works for internal tools, it doesn't work for production Copilot plugins. A key is a secret, and secrets get leaked or shared. Eventually, secrets stop being secret. Microsoft Entra ID authentication is the production pattern you need. You register your function app as an application in Entra ID and configure it to accept tokens issued for that application. Power Platform's custom connector creates an app registration in your tenant, and you grant that app permission to your function. When the connector calls your function, it includes a JWT token that proves it's authorized. Azure validates the token signature, which is cryptographically bound to your function. Only calls from Power Platform with a valid token can reach your code. Unauthorized callers get rejected at the platform level before your code even runs. Network topology matters just as much. By default, your function is publicly accessible and the internet can reach it. That's convenient for testing, but it's a disaster for production. Private endpoints change this equation. You configure a private endpoint for your function, so traffic routes through Azure's internal network. Your function has no public IP address, which means there's no way to reach it from the internet. It exists only inside your VNet and is accessible only to resources that have authorized access to that VNet. This private topology creates a hardened perimeter. Power Platform reaches your function through a private connection, and the downstream systems your function calls are also behind private endpoints. Traffic never leaves the Microsoft network. There's no exposure window and no internet route where packets could be intercepted. The on behalf of flow is a subtler but crucial pattern. When a user interacts with a Copilot, they're authenticated to Power Platform under their own identity. When your function calls a downstream system, it should act on behalf of that user rather than itself. The OBO flow handles this by receiving a token that represents the authenticated user. It exchanges that token for a downstream token that preserves the user's identity. The downstream system logs the action under the user's account, which is how you maintain audit trails and enforce user-level authorization. API management sits in front of your function to apply rate limiting and throttling. A single misbehaving flow can't overwhelm your backend because APIM enforces quotas at the platform level. Your function doesn't need to implement this itself or check rate limits. It doesn't need to decide whether to accept or reject a request because APIM does that before traffic ever reaches your function. Logging completes the picture. Every request should be logged with a correlation ID that traces it through your system. User context and operation outcomes matter, and application insights is where this telemetry lives. It's queryable, it's retentable, and it's auditable. These patterns are the foundation of a secure production plugin. Managed identities, Entra-ID authentication, private endpoints, OBO flows, and comprehensive logging aren't optional if you want to build something professional. The DLP bypass risk and how to mitigate it. Your function is secure, your custom connector is authenticated, and your network is hardened. But there is a structural vulnerability sitting right in front of you that most teams simply do not see until it becomes a massive problem. Custom connectors can be weaponized to bypass your DLP policies. And this is not just a theoretical risk or a what-if scenario. It is documented. Security research has shown that a custom connector can internally reach a service that is explicitly blocked by your organization's DLP policies. The blocked connector stays blocked at the policy level, but the functionality becomes accessible anyway because it is being proxied through something that is not on the block list. Here is how that actually happens in a real environment. Your organization has sensitive data in Salesforce, and your CFO makes a policy decision that Salesforce cannot connect to public cloud storage. A DLP rule is created, Salesforce moves to the blocked category, and suddenly nobody can create flows that move data from Salesforce to Dropbox or OneDrive. The policy is enforced, and on the surface, everything looks fine. But then someone builds a custom connector that calls a webhook hosted in their personal Azure account. The custom connector sends Salesforce data to that webhook, and the webhook writes it to Dropbox. The entire path goes around the DLP rule because the blocked connector never appears in the flow definition. The policy audit shows nothing, the custom connector is marked as business approved, and everything looks legitimate. Now, your sensitive data is sitting in a storage account that is completely outside of your organization's control. This is the structural vulnerability you have to face. Custom connectors are integration points that can proxy traffic to restricted destinations, and unless you treat them as privileged assets, they become escape hatches from your entire governance model. Your first instinct might be to ban custom connectors entirely, but that is the wrong move. That kills legitimate use cases and stops your developers from integrating with systems that Power Platform does not natively support. Banning them does not solve the problem, it just creates pressure for people to find even more dangerous workarounds. The right answer is architecture. The custom connector should never have direct access to your downstream systems. Instead, it should route through a hardened gateway like API management. When you put APM in front of your Azure Functions, it enforces your policies before any traffic ever reaches your function code. APIM becomes your central control point. It validates that the caller is authorized, it checks rate limits, and it logs every single request that comes through. But critically, it can enforce endpoint filtering. You define exactly which domains the API is allowed to reach, and everything else gets blocked. Your custom connector can call your function 1,000 times, but if that function tries to reach a blocked service, APIM rejects it. The policy is enforced at the gateway level rather than at the individual connector. This requires a fundamental mindset shift. You have to stop thinking of the custom connector as a black box that you trust to do the right thing. Start thinking of it as a potential attack surface that is privileged, restricted, and constantly monitored. Operationally, this means you need real governance around who can create these connectors. You cannot let every developer build them. You need a small, specialized team. You also need to limit who can modify them and require formal approval before anything is deployed to production. Every connector must be treated as a tracked asset. The OpenAPI spec for your function becomes part of your enforcement strategy. You do not expose operations that would let someone call restricted services or upload files to arbitrary storage. You do not expose operations that bypass authentication. You design your function's contract with the assumption that the caller might be hostile. This might sound paranoid to some, but it is actually just realistic. Most people do not intentionally try to break the rules, but they do find creative solutions to business problems without understanding the security implications. A hardened perimeter prevents those good intentions from turning into serious security incidents. API management as the security front door. This is where your architecture starts to get sophisticated. API management is the component that takes a collection of scattered security concerns and transforms them into a unified enforcement layer. In the operational reality of this setup, API management sits directly between Power Platform and your Azure Functions. It is the only thing your custom connector can actually reach. Your function does not have a public endpoint, and there is no direct route from the connector to the function code. Everything has to flow through APM first. This is a decisive architectural choice because it makes APM your single point of control. Every request is inspected, logged, and evaluated against your policies before it ever touches your backend. Think about how this simplifies authentication. Your custom connector might use API keys, while your downstream services use Entra ID with certificates, and your internal APIs use OAuth. APIM can accept all three of these types at the edge, normalize them into a standard format, and then pass a clean request to your function. Your function does not need to understand the complexity of certificate validation or OAuth flows. It just receives a header saying the request is from a trusted caller and proceeds with the work. This decoupling makes your entire architecture much easier to maintain over time. The real power of APM emerges when you start using policies. A policy is just a rule that runs on inbound or outbound traffic. You can use them to inject headers, validate JWT tokens, or transform request bodies by stripping out fields your function does not need. You can log every request to a security system for auditing or enforce schema validation, so your function never sees malformed data. This is what we call preventive security. Your function does not get garbage input because APM rejects it at the door. It does not get called by unauthorized users because APM validates credentials before forwarding the request. You do not have to write basic security checks into your code because the gateway has already handled them. Rate limiting and quota management also live at this layer. You can define exactly how many requests per minute an API key can send, which prevents a single misbehaving flow in Power Platform from overwhelming your backend. If a flow starts sending millions of requests, APIM throttles it with a too many requests response. This forces the flow to back off and ensures your function stays available for everyone else. Without this, a simple bug in a flow becomes a denial of service attack against your own infrastructure. APM also allows you to route traffic intelligently. You can set up rules to send traffic from specific IP addresses to a canary endpoint for testing. You can run A/B tests by sending a small percentage of traffic to a new version of your function while the rest stays on the stable version. This gives you granular control over rollouts. Instead of switching versions all at once and hoping for the best, you can move slowly and reduce risk. You should always publish your OpenAPI spec from APIM rather than the function itself. Your function's actual URL might be hidden deep in Azure, and Power Platform should never see it. When Power Platform imports the spec, it only sees the APIM endpoint. This ensures the spec always matches the enforced behavior. You cannot accidentally bypass the gateway because the connector has no idea the function endpoint even exists. This architecture finally answers the big question of how to stop custom connectors from becoming bypass mechanisms. You eliminate the bypass entirely. The connector cannot reach anything except the gateway, and the gateway enforces policies that are immutable to the average user. There is no side channel and no workaround. APIM is the enforcement surface that turns your governance intentions into a technical reality. It is the difference between having a policy on paper and actually preventing data from leaving your environment. This is the point where security stops being a document and starts being part of your infrastructure. Durable functions for stateful workflows. Most of the patterns we have discussed so far follow a very simple logic where a request comes in, the function processes it, and a response goes out immediately. This single execution cycle works perfectly for things like data transformation or basic validation, but real enterprise workflows almost never fit into that tiny box. Imagine your Copilot user needs a multi-step approval for a new project. First, a request is created and routed to a manager, who then takes a few hours to approve or reject it. If they say yes, the request moves to the finance department for a second review, and only after that final decision is the resource actually provisioned or archived. This entire sequence could easily take 3 days to finish, and no HTTP request on Earth is going to stay open for 72 hours. Functions aren't designed to sit idle and wait for days, and if you try to force them to, the system will simply time out and fail. This is the exact point where standard HTTP-triggered functions hit a wall because they are completely stateless by design. Every time a function runs, it starts with a blank slate and has no memory of what happened 5 minutes ago or what the previous step accomplished. When your workflow needs to pause at step 2 to wait for a human to click a button, a standard function has nowhere to store that progress. You could try to build your own state management using external databases and complex timers, but that approach is usually brittle, hard to maintain, and prone to breaking under pressure. Durable functions were built to solve this specific problem by using a collection of specialized functions that work together as a team. The orchestrator function acts as the brain of the operation and defines the entire workflow like a state machine. It decides which step comes next, waits for external conditions to be met, and handles retries if a specific task fails. Because the orchestrator is deterministic and has no side effects, it doesn't make API calls itself, but instead coordinates the entire execution from start to finish. The actual heavy lifting is handled by activity functions, which behave like the standard functions you are already used to. These activities are the ones that call downstream systems, validate your data, or send out notification emails to the team. If an activity function fails or times out, the orchestrator sees that failure immediately and decides whether to try again or trigger a rollback. Everything starts with a client function, which is the entry point that triggers the entire orchestration. When a user asks for that approval workflow, the client function kicks off the process and hands back an instance ID right away. The user sees a message saying their request was submitted with a specific tracking number, giving them instant feedback while the actual work happens asynchronously in the background. This architecture completely flips the traditional model on its head. Instead of making a user wait for a complex process to finish, the workflow moves forward on its own timeline without blocking the interface. The user can check the status whenever they want, or the system can send a webhook callback once the final step is complete. One of the biggest advantages is that the orchestrator treats the entire workflow as a piece of data that it can track. It knows exactly which activity is finished and where the process stands at any given second. If the function app crashes or Azure moves your instance to a different server, the orchestrator has a full record of the state and can pick up right where it left off. You never lose work, and you never have to restart a 3-day process from the very beginning just because of a minor system update. Resilience is also much easier to manage because retries are handled automatically by the platform. If a service is temporarily down or hitting a rate limit, you can set a retry policy with exponential backoff at the orchestration level. This means every single activity gets that same level of protection without you having to write custom error handling code for every individual function. Durable functions really show their value when you need to handle fan-out and fan-in scenarios. If your workflow needs to run 5 different validation checks at the same time, the orchestrator can spawn all 5 activities simultaneously rather than waiting for them to finish one by one. Once every parallel task reports back with a result, the orchestrator fans back in and moves to the next phase of the project. This type of parallel execution cuts down on total latency and makes your enterprise workflows feel significantly faster. Status tracking is built directly into the runtime, so you don't need to build custom tables to see if a process is still running. You can simply query the system for a specific instance ID to see which activities are done and what the results were. This is the professional way to handle the 80% of business logic that doesn't fit into a simple request-response window. You stop fighting against the limitations of HTTP and start using a tool that was actually designed for long-running, stateful work. Latency optimization. Every millisecond counts. While durable functions are great for those long-running background tasks, most of your Copilot interactions need to happen in real time. When a user types a question into a chat box, they expect a response to appear almost instantly. In these synchronous moments, your ability to shave off every possible millisecond becomes your biggest competitive advantage. For simple operations like a quick database lookup or a validation check, you should be aiming for a warm invocation latency of under 100 milliseconds. If the task is more complex and involves calling multiple systems or aggregating large amounts of data, you should still try to stay under 300 milliseconds. Once you cross that half-second mark, users start to feel the lag, and if a response takes longer than a full second, you have likely lost their attention entirely. These numbers aren't just guesses, but are actually based on how the human brain perceives a system as being responsive. We expect an immediate acknowledgement of our input within about a tenth of a second, and anything slower than that creates a feeling of friction. If your architecture can't deliver that sub-100 millisecond response on the happy path, your users will start to doubt the reliability of the entire tool. The foundation of a fast system is smart connection management. As we discussed earlier, you should never create a brand new database connection for every single request because the overhead of handshakes and authentication is far too high. By using a pooled connection that stays alive between requests, your code can start running the actual query immediately without waiting for the network setup. The same logic applies to your HTTP clients, where reusing a single instance for all outbound calls eliminates the need for repeated TLS handshakes. Where you put your infrastructure matters just as much as the code you write. If your function is sitting in a data center in Virginia but your database is located in London, every single query has to travel through undersea cables across the Atlantic. That physical distance adds 50 to 100 milliseconds of pure travel time before your database even sees the request. By co-locating your functions, storage, and databases in the same region, you can drop that round-trip time down to single digits and save a massive amount of time for free. Caching is another way to amplify your speed by avoiding the network entirely. Reference data and configuration settings that don't change often should be stored in memory as static fields within your function code. Accessing a variable in memory takes microseconds, which is thousands of times faster than making a round trip to a database. For data that needs to be shared across multiple instances, a distributed cache like Redis is a great middle ground that is still much faster than a traditional disk-based query. It is important to remember that latency is never a single, consistent number for every user. Some requests will hit the cache and be lightning fast, while others will miss and have to fetch fresh data from a slow downstream service. This is why you cannot rely on averages, because an average of 300 milliseconds might be hiding a few requests that take 5 seconds to finish. Users don't remember the average experience, but they definitely remember the one time the system felt broken and slow. You need to focus your optimization efforts on tail latency, specifically looking at your P95 and P99 metrics. If your P99 latency is 5 seconds, it means 1 out of every 100 requests is failing the user experience, which happens about once per conversation for an active user. When a user hits that slow path, they don't care that the other 99 requests were fast. They just feel like the system is unreliable. To fix this, you need deep instrumentation that shows you exactly how long each dependency and code path is taking. Once you can see which specific API call or database index is causing the slowdown, you can actually do something about it. Without that visibility, you are just guessing and hoping for the best. This level of detail is what separates a basic function that technically works from a Copilot experience that feels truly instant. Monitoring and observability. Blind optimization is a waste of time. You need eyes inside your system. Application Insights is where those eyes live. It serves as the standard telemetry platform for Azure workloads, and it becomes your primary diagnostic tool for understanding how your Copilot plugin actually behaves in production. Not how you think it behaves, not how it behaves in your test environment. You need to see how it actually behaves when real users interact with it. Send execution time data to Application Insights. How long does each function invocation take from start to finish? And how long does the database query or the downstream API call take? The more granular you go, the better your visibility. You are building a map of where time actually gets spent. This level of detail is how you find the bottleneck that is limiting your whole system. Sometimes the problem is obvious, like a database query that takes 2 seconds, but other times it is subtle, like a cache miss that cascades into 5 sequential lookups. Without instrumentation, you are just guessing. With it, you see the actual behavior. Correlation IDs are how you track a single user request through your entire system. Your Copilot user types a question, and that question generates a unique correlation ID that travels through Power Platform and into your custom connector. That ID enters your function, and your function logs that ID with every operation it performs. When your function calls your database, that query includes the correlation ID, and when it calls a downstream API, that request includes it too. Later, when you are investigating why a user request failed, you search for that correlation ID across all your logs. You see the entire journey. You see exactly where it broke. This is how you move from something went wrong to this specific API call returned a 500 at 14:32:17 UTC. Custom metrics go beyond raw performance data. You care about business outcomes, not just technical metrics. Track invoices validated per minute, or approval workflows completed today, or even your cache hit rate percentage. These metrics answer the question of whether your system is actually working for your users. A 100 millisecond response time is great, but if only 60% of validation requests succeed, your system is failing. Business metrics surface the problems that matter. Alerting strategy separates operational maturity from reactive firefighting. Alert on P95 and P99 latency spikes, or when your error rate exceeds a threshold, or even on cold start frequency. But do not alert on averages. An average latency of 300 milliseconds tells you nothing, because it masks the fact that half your requests take 100 milliseconds and the other half take 500. Alert on the tail. Alert when something changes unexpectedly. Alert when your system violates a known pattern. This is how you catch problems early instead of discovering them when users start to complain. Diagnostic settings on your function app export logs to log analytics. Application Insights captures application telemetry, while log analytics captures platform-level logs for when instances scale, when deployments happen, or when quotas are hit. Together they give you complete visibility. Logs live in log analytics for years, which means you can query historical data or build long-term trend analysis. You can prove that a change you made 6 months ago improved stability. Azure Monitor workbooks tie this together into dashboards. A workbook is a canvas where you build custom visualizations. You add charts showing latency trends, gauges showing current error rates, and tables listing your slowest operations. You can even add heat maps showing traffic patterns by time of day. These workbooks become the operational brain of your system. When something feels off, you check the workbook. You see the actual behavior. You adjust. The discipline here is measurement without obsession. You need visibility, but you do not need to track everything. Start with latency per operation, error rate, and cold start frequency. Add business metrics relevant to your domain and refine from there. The goal is to catch degradation before it becomes an outage. This is how you move from hoping your system works to knowing it works. Testing the integration from unit to end. Theory breaks on contact with reality. Everything we have built, from the function and the OpenAPI spec to the security infrastructure, needs to survive actual usage. That is what testing does. It bridges the gap between this should work and this actually works. Start with unit tests. Your CE business logic needs full coverage. validate invoices, transform data, and apply business rules. These tests run fast and they run locally. They mock external dependencies, so you are not actually calling your database or hitting external APIs every time you run the test suite. This is standard practice. But for serverless functions, unit tests become your primary validation tool. You cannot easily debug a cold start issue in production, and you cannot step through your code with a debugger while it is processing a live Copilot request. Unit tests catch logic errors before they escape. Integration tests are where most teams stumble. They test the contract between your code and the external world. Here is what matters. Call your function via HTTP and invoke it exactly the way the custom connector will invoke it. Send a real HTTP request with real headers and a real payload, then capture the response. Validate that the response schema matches your OpenAPI spec. This is crucial because your OpenAPI spec defines what downstream systems expect. If your function returns a field with the wrong type or misses a required field or includes extra fields that the spec does not document, the custom connector might break. Integration tests catch this. They validate the contract, not the internal implementation. Load testing reveals what unit tests hide. Your function handles one concurrent request perfectly, but what about 50 or 500? Load testing tools like K6 or Azure. Load testing simulate realistic concurrent load. You define a scenario where 50 users each make 10 requests with realistic think time between them, and then the tool hammers your function. It shows you where your latency degrades. It shows you where you hit resource limits. It shows you whether your rate limiting works. It shows you your actual system behavior under stress, not imaginary behavior in a lab environment. Here's the critical part. Test with real user language, not API syntax. Do not test by calling your function with a perfectly formatted JSON payload. Test by simulating how Copilot actually invokes your function. Copilot sends natural language, and the LLM interprets it and fills in parameters. Sometimes it interprets ambiguously, and sometimes it misses context. You want to find these problems in testing, not in production. A Copilot plugin that works perfectly with structured input but fails with natural language variations is broken. Load testing that does not capture this reality is just theater. The handshake between Power Platform and Azure is a specific test. Your custom connector maps to your function, it transforms input, and it handles errors. You need to validate that this mapping works. Create a test flow in Power Automate or Power Apps, call your custom connector, and verify that the call succeeds. Verify that the response is processed correctly by the low-code layer. This test is part integration test and part sanity check. It catches configuration problems that code tests miss. A firewall rule that blocks your connector from reaching your function will not show up in a unit test, but it will show up in a connector test. Deployment slots let you test in production without affecting users. You deploy a new version to a staging slot, you run your tests against staging, and you validate the behavior. You do load testing against staging, and then you flip the production slot to the staged version. Now your production traffic routes to the new code. If something breaks, you flip back to the previous version in seconds. This is continuous deployment. It is how you iterate safely. The testing discipline separates teams that ship stable Copilot plugins from teams that debug issues in production at 2 in the morning. Testing is not about passing tests, it is about confidence. It is about knowing that your plugin will work when real users depend on it. Versioning and evolution. Your first Copilot plugin is finally in production and everything is working exactly as planned. Users are starting to depend on it and teams have already built their daily workflows around the tool. But now you need to add a new feature, or maybe you found a bug that needs fixing. This is the moment where versioning discipline separates a professional, maintainable system from one that becomes fragile and broken. Here's the hard truth about software. Once your function is in production, it doesn't really belong to you anymore. It belongs to the flows and systems that call it. Those flows have specific dependencies, and they expect your parameters to mean the exact same thing every single time. You cannot casually change those expectations without consequences. Every update you make either respects those existing dependencies or it completely breaks them. The operation ID is your contract with the rest of the world. When you define an operation in your OpenAPI spec with an ID like validate invoice, that name becomes your permanent anchor point. Power Platform flows reference that specific ID to function, so if you change it, those flows will break silently. They will try to call an operation that no longer exists, and the users will only see a failure they don't understand. They will blame the system and stop trusting your tool, which is why you should never change an operation ID. It must stay stable for the entire life of that operation. If the behavior changes fundamentally, you aren't modifying an old tool, you are building a new one with a new ID. This is where semantic versioning becomes your best friend. Your API needs a version number starting at 1.0.0. The first number represents the major version, the second is the minor version, and the third is for patches. When you add a new operation, you bump that minor version to 1.1.0. Clients can upgrade whenever they feel like it because nothing broke, since you only added features instead of removing them. When you fix a bug in the code without changing the contract, you just update the patch version. However, if you break the contract or change how a flow needs to behave, you must move to version 2.0.0. This tells everyone downstream that something big changed, and they need to review their implementation. Using separate function apps or deployment slots lets you run multiple API versions at the exact same time. Your version 1 app stays stable and serves your current production traffic, while your version 2 app gets all the new features. You can deploy the new version to a staging slot to validate it before running both versions side by side in production. The connector for version 1 keeps talking to the old app, and the connector for version 2 reaches the new one. This lets teams migrate at their own pace, and nobody is forced to upgrade until they are actually ready. This gradual transition is the only way to move the platform forward without breaking the systems people rely on. The OpenAPI spec itself is a piece of history that needs proper version control. You should store it in Git right alongside your function code so you can track every change in your commits. When you release a new version of your API, make sure to tag the commit that contains that specific spec. Later on, when a teammate asks what changed between the old and new versions, you will actually have the answer. You can compare the files and see exactly which operations were added or modified. This is how you communicate clearly with other teams and maintain a record of how the system evolved. Deprecation paths are where most teams start to struggle. Eventually, you will have an operation that is no longer the best way to solve a problem because a better version exists. You might want to delete the old one immediately, but you have to remember that people are still using it. Instead of deleting it, mark it as deprecated in your spec and explain why. Suggest the new alternative and give everyone a clear timeline for when the old version will disappear. If you tell teams the operation will be gone by December, they have months to plan their migration. When that date finally arrives, they are ready for the change, and the transition happens without any drama. This level of discipline turns your API from a source of constant frustration into a reliable foundation. It is the difference between being afraid to touch your code and having the confidence to evolve. You can move faster because you have a strategy that respects the people using your work. Your function is never truly finished, but it should evolve with purpose instead of moving in a state of chaos. That is what makes a system professional. Cost optimization and right-sizing. Performance and security are always the top priorities, but they have to live inside a real-world budget. Every choice we have made so far, from using always-ready instances to setting up comprehensive logging, comes with a price tag. The real question isn't whether you can afford this setup, but whether you are paying for it in the most efficient way possible. Flex consumption billing is calculated using two main factors: how long your code runs and how many times it gets called. You are essentially paying for gigabyte seconds. If you run a function with 512 megabytes of memory for 2 seconds, that counts as 1 gigabyte second. You also pay a small fee for every million times the function is triggered, which is usually around 40 cents. If you optimize both of these areas, you can keep your bill under control. But if you ignore them, your costs will start to spiral. Always ready instances provide a baseline cost that you need to account for. Let's look at the actual numbers to see how this works. A single instance with 2 gigabytes of memory costs a tiny fraction of a cent per second, but that idle time adds up fast. Keeping one instance warm all day and night costs about $288 every month. If you need 2 instances, that jumps to $576. For that same price, you could almost run a premium plan with a dedicated instance. If you are constantly running multiple always-ready instances, the math changes and premium might actually be the cheaper path. Most teams make a huge mistake by picking their memory size based on a gut feeling. They assume a small function only needs 512 megabytes because the data it processes is tiny. What they miss is that Azure ties your CPU power directly to how much memory you allocate. That small instance might take 3 full seconds to finish a task because it has very little processing powers. If you bump that up to 2 gigabytes, the extra CPU might finish the same task in 600 milliseconds. Even though the larger instance costs more per second, the faster finish time can actually save you money on your baseline costs. You end up with a lower bill and a response time that is 3 times faster. This is the strange reality of serverless economics, where the more expensive option is sometimes the cheaper one. Scaling up to a bigger instance can be more cost-effective than scaling out to many small ones. You have to run the actual math for your specific workload instead of just guessing. Azure Cost Management is the best tool for doing this math correctly. It lets you break down your spending by specific operations or time periods so you can see exactly where the money is going. You can find the functions that run all the time but finish quickly, which are usually very cheap. You can also spot the rare functions that take forever to finish and cost a fortune every time they run. Once you identify those expensive operations, you can target them for optimization. Faster code reduces your bill, and better caching means you don't have to run the code as often. Batching is your most powerful weapon when it comes to saving money. If your Copilot needs to check 10 different invoices, do not make 10 separate calls to your function. You should send all 10 invoices in one single request, so the function only has to run once. This means you only deal with one cold start and 1 unit of billing instead of 10. A single batch operation is almost always faster than 10 separate round trips over the network. It pays for itself immediately by cutting down on invocation charges and execution time. Reserved capacity is something you should consider once your traffic becomes predictable. If you know for a fact that you will run 5,000 calls every day, you can stop paying the standard on-demand rates. Azure savings plans allow you to commit to a certain amount of usage in exchange for a 20% discount. You are trading away some flexibility for a lower price, so the math only works if you actually use what you promised. If you overestimate, you are paying for air, but if you get it right, it is the cheapest way to run at scale. Optimizing your costs isn't something you do once and then forget about. It is a constant cycle of measuring your results and making small adjustments. Improvements in performance almost always lead to a lower bill, and looking at your costs often reveals where your code is slow. These two goals actually work together. Usually the fastest function is also the cheapest one to run, so you should always be chasing both. Deployment and CI/CD. Getting code from your laptop to production safely is only half the battle, because the other half is making sure you don't break everything once it's actually live. This is where deployment discipline separates the high performers from the teams that only ship once a quarter because they are terrified of a system crash. Everything starts with infrastructure as code. Your function apps, your key vaults, and your storage accounts are all defined as code rather than being clicked into existence. You might use Bicep if you are staying native to Microsoft, or you might choose Terraform for a multi-cloud approach, but the core principle never changes. You aren't clicking buttons in the Azure portal to provision resources anymore. Instead, you declare your infrastructure in code, check it into Git, and version it just like your application logic. When you deploy, that code drives the environment, which makes your deployments repeatable across dev, test, and production. By using the same template for every stage, you ensure that if a feature works in your test environment, it will work in production because the underlying infrastructure is identical. Automation is what makes this whole process reliable. When you push code to Git, a pipeline in GitHub Actions or Azure DevOps triggers automatically to run your unit tests. If those tests fail, the deployment stops immediately, so you never ship broken code to your users. If they pass, the machine runs integration tests against a staging environment and builds your deployment package. It validates your infrastructure code and checks for common mistakes before anything touches a live server. This entire flow is automatic, repeatable, and auditable. A deployment isn't a person running manual commands on a Friday afternoon, but a machine following a strictly defined process. This shift to automation is actually where your risk decreases. Manual deployments are where mistakes happen, like when someone misses a configuration step or accidentally deploys the wrong version of a file. Automated pipelines remove that human element entirely. The same process runs every single time, so you know exactly what is happening under the hood. Deployment slots give you an extra layer of safety. Your production slot handles the live traffic, while your staging slot acts as a perfect mirror where you can test new code. You deploy the new version to staging, run your full load tests, and validate that the system is stable. Once you are ready, you perform a swap. Staging becomes production, and production becomes staging in an instantaneous transition. If something goes wrong after the swap, you just flip it back. The old code is still sitting there in the staging slot, so you can revert in seconds without an outage. This is how you ship with confidence. Security is non-negotiable, which means secrets never go in your code. If a database password or a connection string ends up in your Git repository, your entire system is compromised. Anyone with access to that repo now has the keys to your data. You should keep those secrets in Azure Key Vault and let your function authenticate using a managed identity. The secret never touches your source code and it never appears in your logs. It stays protected by Azure's encryption and access controls at all times. Environment variables are different because they represent configuration that is safe to share. Your function needs to know which database to talk to, but that answer changes depending on where the code is running. In dev, the variable points to a test database, but in production, it points to the real thing. The code stays exactly the same, but the behavior changes based on the environment variables you've set. Your rollback procedure is more important than the deployment itself. If you use slots, a rollback is just a 30-second swap, but if you don't have a tested plan, you'll end up improvising under pressure. When the team is stressed during an outage, they make mistakes that make the downtime even longer. You need to document your rollback steps and run a dry run every quarter. You have to know exactly what to do before a crisis actually hits. This level of discipline turns deployment from a high-stakes gamble into a boring, routine operation. You end up shipping more often while breaking things less, and when something does go wrong, you recover before anyone notices. Real-world scenario: Invoice validation plugin. Architectural principles can feel abstract until they meet a real business problem. Let's look at how a finance team builds an invoice validation plugin to see how these different pieces actually work together. The finance team usually spends hours answering the same basic questions about vendor payments and approval thresholds. Employees want to know if an invoice is valid or if a specific vendor has been paid yet. Right now, answering those questions means logging into an old accounting system and digging through spreadsheets, which takes about 10 minutes per request. The team is essentially drowning in manual, low-value work. A Copilot plugin changes that dynamic entirely. An employee can simply ask Copilot if a specific invoice is valid, and the system routes that request to the validation plugin. The plugin returns a clear, structured answer in less than 500 milliseconds. The employee gets what they need instantly without bothering the finance department. The OpenAPI spec for this plugin defines 3 specific operations. You have validate invoice to check status, get invoice details to pull record information, and flag invoice for review for manual audits. These names are chosen carefully as verb-noun pairs so the LLM can easily tell them apart. When a user asks for information, the model routes to the details operation, but when they ask for a status check, it hits the validation logic. The engine behind this is a cpice function running on Flex consumption with always-ready instances. Instead of running all the logic in one place, it uses durable functions to coordinate the workflow. An orchestrator function starts by calling 3 separate activities at the same time. One checks the accounting system, another verifies the vendor credentials, and the third looks for duplicate submissions. Because these checks run in parallel, the orchestrator only waits for the slowest one to finish before moving on. If the invoice passes every check, the system calculates the approval threshold and returns the result. If it fails anywhere, the process stops and reports the error immediately. The orchestrator packages all of this into structured data that flows back to the Copilot. The user doesn't just see a yes or no, but a clear explanation of why an invoice was rejected or why it needs a manual review. API management sits in front of the whole operation to keep things stable. The custom connector talks to APIM instead of hitting the function directly, which allows you to enforce rate limits. This prevents a single user from overwhelming the backend with too many requests. APIM also handles the heavy lifting of security by validating tokens and injecting correlation IDs into every request. It even checks the data coming back from the function to make sure it matches the expected schema. If the function returns something messy, APIM catches it before the Copilot tries to read it. Speed is the main goal here, so the team uses several optimization tricks. Since vendor credentials don't change very often, they are cached directly in memory on the always-ready instance. The first request might be a bit slower, but every request after that hits the cache for near-instant results. Connection pooling keeps the database links open so the system doesn't have to waste time creating new ones for every query. By running the 3 main checks in parallel, the total latency drops from 3 seconds down to about 300 milliseconds. Monitoring keeps a close eye on 3 specific areas. If the validation failure rate climbs above 5%, an alert tells the team that the accounting system might be down. If the P99 latency goes over 1 second, the team knows they have a cache issue or a system slowdown. They also track cold starts to make sure the always-ready instances are doing their job. If startup times start to creep up, it means a deployment changed something that made the app too heavy. The result is a system with total traceability. Every single request has a correlation ID that follows it through APM, the function, and the database. If a user asks why their invoice was denied 3 weeks later, the finance team can pull the logs and see exactly which check failed. This is a plugin built to scale. It is fast, it is auditable, and it is easy to maintain because every component has a specific job. When you combine always-ready instances with durable functions and APM governance, the whole system becomes much stronger than its individual parts. Common pitfalls and how to avoid them. Most teams don't fail because they don't understand the architecture, but rather because they skip steps that seem optional until the moment they become catastrophic. These pitfalls are essentially the tax you pay for cutting corners during development. The first major mistake is writing your OpenAPI spec for the wrong audience. You're a developer who understands your own code, so you write clear documentation for other humans, but the model doesn't read like a programmer, it reads like a user. When you write returns customer records filtered by status, you've said something technically correct, but the model just sees a generic operation for retrieving data. When 3 different operations in your spec all do similar things like search, get, and fetch, the model gets confused and starts picking between them at random. Your Copilot calls the wrong operation, the flow fails, and the user blames the bot for being broken. What actually happened is your spec was too ambiguous for the LLM to navigate. You need to write descriptions that explain when to use an operation instead of just what it does. If you write use this when you need to find customers by their name or company, the model finally has the language it needs to route the request correctly. Choosing not to use Flex Always Ready is like leaving your car running in the driveway all day just to avoid a 2-second startup delay. You might be solving the cold start problem, but you're also burning money and wasting resources for no reason. Classic consumption scales to 0, which means if your plugin sits idle for an hour and a user finally makes a request, the function has to spin up from scratch. The user experiences a massive lag spike while they wait for the system to wake up. Flex with Always Ready keeps a small instance warm at a fraction of the cost of a premium plan, making it the obvious choice for any professional setup. Teams often skip this because they think they'll optimize the performance later, but later never actually comes. They end up living with 5-second startup delays that compound into thousands of lost conversations, all while an Always Ready budget would have only cost about $200 a month. Embedding secrets directly in your code is a fast way to lose your job. Your function needs a database password, so you hard-code it and check that code into Git, which allows anyone who clones the repository to read your credentials. They can connect to your production database and export your customer data to the internet before you even realize there's a leak. You didn't mean to expose the data, but you took a shortcut that bypassed basic security. Azure Key Vault exists for this exact reason, and you need to use it. Your function should authenticate to the key vault using a managed identity so the secret is returned securely without ever touching your source code. Never hardcode your secrets because this isn't just a best practice, it's a fundamental requirement for staying employed. Blocking calls in your functions will completely waste your investment in Always Ready. When your function calls an external API and the thread sits there waiting for a response, that Always Ready instance is being consumed while doing zero actual work. If the next request comes in while the thread is blocked, there's no available instance to handle it, so a new one has to spin up. This creates a cold start and a latency spike that defeats the entire purpose of keeping the instance warm in the first place. You need to use async and await to make your API calls asynchronously so the thread can yield. This allows another request to use that same thread while the first one waits for its data to come back. Concurrency is what multiplies your capacity, and blocking code just throws that multiplier away. Flying without monitoring or logging is like flying a plane blind. Your function might work perfectly in a test environment and the deployment might go fine, but 2 weeks later, users start reporting that requests are failing silently. Your function isn't throwing any obvious errors, it's just returning empty results, and without logs, you have no way to know why. You'll spend 3 days guessing at the cause when you could have seen the answer in 30 seconds. With proper logs, you would immediately see that a downstream dependency changed its response format and broke your parsing logic. Monitoring is not an optional add-on, it's insurance against spending your entire week debugging problems that should have been visible from the start. If you don't version your OpenAPI spec, your evolution will eventually turn into total chaos. The moment you modify an operation or change a parameter type, you break every existing flow that depends on the old structure. The person who created that flow has no idea what changed or why their automation suddenly stopped working, so they file a support ticket and wait for an apology. You end up reverting the change and realizing you haven't actually made any progress. You need to version your spec and track every change you make. When you modify a feature, bump the version number and communicate that shift to your users. This gives teams the time they need to adapt so you can evolve the system without breaking everything in your path. These aren't subtle problems that only show up for experts. They are common, preventable, and incredibly expensive if you choose to ignore them. Scaling from pilot to enterprise. Your invoice validation plugin is finally live and stable, and the finance teams are actually using it. But now the CRM team wants something similar, the HR team wants a bot for employee queries, and the logistics team is asking for shipment tracking. One single plugin proved that your architecture works, but now you suddenly need 10 of them. If you don't have a scaling strategy, you're going to spend the next year reinventing the same wheels over and over again. You'll keep making the same decisions about APM configurations and function structures while making different mistakes in every single implementation. By the time you get to plugin number 5, you'll be drowning in maintenance. This is the point where pattern libraries separate the mature organizations from the chaotic ones. A pattern library is really just a collection of reusable templates that keep you from starting at zero every time. Since you've already standardized the invoice validation plugin, you should extract that logic into a template. Create a generic scaffolding that includes your HTTP triggers, your durable functions orchestrators, and your standard error handling. When a developer needs to build a new plugin, they start from this template instead of a blank screen. They can focus entirely on the business logic because all the plumbing is already handled and correct. Your OpenAPI templates should follow this same logic. Since you've already learned what the LLM understands, you can create a canonical structure for all new operations. This ensures your specs stay consistent, your naming conventions remain the same, and the LLM never runs into any surprises. Bicep modules allow you to encapsulate your infrastructure patterns so they can be deployed reliably. Instead of every developer trying to write their own key vault setup or APIM configuration, they should just call a pre-made module. The module handles the complex details while the developer just provides the parameters. If a dev needs a new plugin that handles 1,000 requests a day, the module creates the right instance size and applies the necessary security policies automatically. The developer doesn't have to write a single line of infrastructure code because they just declared what they needed and the system delivered it. True consistency only emerges when you make reuse the easiest path forward. Centralizing your authentication and authorization removes a massive amount of friction from the development process. You shouldn't have every single plugin managing its own identity system. Instead, you should create a shared authentication policy within APIM so that when a request arrives, the security check happens exactly once. The request then carries a trusted identity token to every downstream service. This centralization makes your governance much simpler because you have one single place to audit access or revoke credentials. If compliance suddenly requires multi-factor authentication, you only have to implement it in one spot. Teams won't try to bypass this security layer because you've made it the most convenient way to build. Implementing governance for custom connectors is the only way to prevent shadow integrations from taking over. Without a process in place, a developer might create a custom connector for a new API and deploy it to production without anyone ever seeing it. You'll have no idea it exists, even though it might be reaching a blocked service or exposing sensitive company data. You need a simple approval workflow where developers submit their connector requests for a quick security review, Once the connector is approved, it gets added to the pattern library for other teams to reuse. This doesn't actually slow down development, it actually speeds things up because developers can build on top of approved patterns instead of making up ad hoc solutions on the fly. A self-service portal can let developers request new functions without having to wait for your team to manually intervene. The portal is just a simple form where a user describes what the function needs to validate and how much traffic they expect. That form feeds directly into a pipeline that builds the function from your template, generates the spec, and deploys it to a dev environment. This gives the developers instant scaffolding to work with while giving your team total visibility into what's being built. It allows everyone to move faster without sacrificing the quality of the underlying system. Runbooks are your operational insurance for when things go wrong in the middle of the night. When a plugin fails at 2 in the morning, the engineer on call shouldn't have to understand every detail of the architecture to fix it. The runbook should tell them exactly what to do if latency spikes or if a cache hit rate drops below a certain level. If the vendor credential cache expires, the instructions tell them to restart the always ready instances. The engineer follows the steps and fixes the problem in 10 minutes instead of spending 2 hours investigating the root cause. Runbooks capture the collective knowledge of everyone who has ever debugged the system, and they are the difference between reactive firefighting and a confident response. This is the path for scaling from a single pilot plugin to a full enterprise platform. You don't get there by hoping every team figures out the same lessons on their own. You get there by building those lessons directly into the infrastructure and the processes that scale with you. The strategic shift from low-code toys to enterprise engines. We have walked through the entire architecture together. You understand the hosting choices, the security perimeter, the monitoring discipline, and the deployment rigor. But these are not just abstract concepts. They represent a fundamental shift in how enterprise AI actually gets built. Low-code platforms changed the game by democratizing automation. Before Power Automate existed, you needed enterprise architects to design integration solutions at astronomical hourly rates. Low-code put that power into the hands of business teams. It was genuine innovation. It reduced friction and accelerated delivery. But it also created a dangerous assumption that low-code can do everything. The assumption is that you can automate anything with enough Power Automate flows. That assumption breaks the moment you hit sophisticated business logic. This is where the Fusion developer model emerges. It is not about low-code replacing professionals, and it is not about professionals dismissing low-code. Instead, professionals use low-code where it excels, for orchestration, coordination, and connecting systems. Then they use pro-code where it actually matters, for heavy computation, complex transformations, and strict business rules. The Copilot plugin architecture you have learned is the physical manifestation of that fusion. Power Platform handles what it was designed for. Azure Functions handles what requires real engineering. Teams that master this architecture build things their competitors cannot replicate. A competitor might see your Copilot plugin working smoothly and decide they want one too. They can build a basic version in a few weeks using standard connectors. But if your plugin handles edge cases through sophisticated CPOS logic, they cannot copy that quickly. If it maintains sub-second latency through Flex Always Ready configurations or governs data access through APM policies and managed identities, it will take them months to catch up. By the time they figure it out, you have already iterated. You have added new features. You have become reliable. You have gained a competitive advantage that compounds over time. This advantage does not come from raw intelligence or some secret technology. It comes from discipline. It comes from understanding that every architectural decision serves a specific purpose. Choosing always ready over cold starts or using durable functions instead of nested flows is intentional design. It is not accidental emergence. The investment multiplies across every plugin you build. When you build your first plugin with proper infrastructure, you invest heavily in OpenAPI, spec design, APM configuration, and monitoring. The initial bill is substantial, but the second plugin reuses everything. The infrastructure is already there, the patterns are documented, and the team understands the playbook. The second plugin costs a fraction of the first. By the time you reach the 10th plugin, you are deploying at a cadence that smaller, less disciplined teams simply cannot match. Infrastructure investments compound. Security and governance are not afterthoughts in this model. They are built in. You are not trying to bolt on compliance after the architecture already exists. You are designing policies into APM from the very start. You are not wondering who has access to what. You are using managed identities so every access point is auditable and revocable. You are not hoping someone remembers to log important events. You are capturing correlation IDs and streaming them to application insights automatically. The cost of these controls is low when they are part of the foundation. The cost of retrofitting them later is astronomical. Cost optimization becomes a continuous discipline rather than a crisis event. You are not discovering 6 months down the line that your baseline costs are too high. You are tracking costs weekly. You are right-sizing memory based on actual execution patterns. You are using cached data to reduce expensive downstream calls. These micro-optimizations compound. Over a year, they save tens of thousands of dollars in infrastructure spend. The real value is not any individual plugin. It is the reusable infrastructure and the patterns that enable rapid innovation across dozens of plugins. You have built a platform. New capabilities that used to take 3 months to deliver now take 3 weeks because the foundation is solid. The foundation handles the scaling, the security, and the monitoring. Teams building on top can finally focus on business logic instead of infrastructure. This is what separates organizations that just use AI tools from organizations that build AI platforms. You have the blueprint, you understand how Flex consumption eliminates cold starts. You know how to write OpenAPI specs that the LLM actually understands. You have learned to secure your work through APM and managed identities. You have seen how to scale from one plugin to an entire enterprise platform. Start with one high-value workflow. Do not pick the easiest problem. Pick the one that matters most to your business. Validate the architecture on something real. That first plugin will teach you what works and what does not. It will show you the operational reality behind these design principles. Invest in OpenAPI specs and API management early. They might feel like overhead when you are shipping your first plugin. By your third plugin, they will have paid for themselves through reduced maintenance and faster iteration. Monitor everything obsessively. You cannot optimize what you cannot measure. Latency, errors, cold starts, and cache hit rates all matter. If it matters operationally, you need to measure it. Let the data guide your next move. Connect with the community, share your patterns, and learn from the mistakes of others. The Fusion developer model is still emerging. Teams are figuring this out in parallel right now. What you learn becomes valuable to others, and what they learn will accelerate your next iteration. Subscribe to the M365 FM podcast for the latest on Copilot, Azure, and the future of enterprise AI.